through the chapter. Again, I'm just going to be pointing out some of the interesting features of capacitors. So we're going to be doing circuits coming up pretty soon. This is the circuit element for a capacitor. We use either one of these. A capacitor is kind of like a battery. It's a way to store charge. So you'll have two conducting plates in some geometric configuration. Maybe they're parallel plates, maybe they're two cylinders, two spheres. You've got two conductors and you want to store charge on them. And we define, this is a definition, the capacitance of a capacitor is how much charge you can store on it per volt that you apply. So you apply a voltage that forces charges onto your conducting plates, and the capacitance is how much charge you can store per volt that you've applied. So capacitors are, you could kind of think of them like batteries. They're kind of like batteries. They're more for energy storage than I would say, like a battery provides a continuous current, a continuous voltage. And if I want to run my computer off my battery, then that battery's, like I said, providing continuous energy, continuous current to the computer. A capacitor will discharge pretty quickly. So it's like you got a whole bunch of energy stored and it's more like an explosion. All the energy will discharge if I can open a circuit or close a circuit really quickly. So they're crappy batteries. Let's put it like that. Capacitance is measured in farads, which is 1 coulomb per volt, named after Michael Faraday. Almost a quarter of what we do this semester was developed by Faraday. Okay, so the simplest kind of capacitor we could have is a parallel plate capacitor. Now in that lab, I mentioned this earlier, in this lab, your last assignment, the last part of it was creating a parallel plate capacitor, but you really didn't. You created two finite lines of charge. And a plate capacitor should be infinite plates of charge. So that's why when you got your difference at the end, the what do we call it, the percent difference, some of you ended up with like a 30% difference. It's because it wasn't a very good parallel plate capacitor. You just had lines instead of areas of charge. So ideally, these would be infinite planes of charge. Then we know what the electric field is from an infinite plane. We've solved that problem a couple of times using Gauss's law. We even did one like this where we had two infinite planes and we said we have a constant electric field. E is sigma over epsilon naught in between here, where sigma is our charge density. Well, as long as this distance in between these finite plates is small compared to the size of the plate, then we have a nearly constant electric field inside. So on the outside, we might have electric field that kind of bows out. This is called edge effects. But here in the middle, we have a nearly constant electric field, and that has value sigma over epsilon naught, where sigma is the charge on the positive plate divided by the area of the positive plate. So that could be rewritten as Q over epsilon naught A. That's our electric field in between the plates, in the middle of the plates. We know when you have a constant electric field, you guys did this in your lab, V is approximately ED. So that's VAB. That's not change in V. That's not final minus initial. This is a weird notation we use for initial minus final. That's why there's no negative sign here. So the voltage in magnitude difference across the plates is ED. So just plugging in here, we get this. And then by definition, capacitance is Q divided by V. So this is the formula we use for capacitance of a parallel plate capacitor. I was just mentioning right before we started recording, I want you guys to remind me of this when we get near test 2. On the equation sheet for test 2, you will need this formula. And I done goofed when I typed this up 5-6 years ago. That epsilon naught should be on top right there in this formula, not on the bottom. That is an error. And I don't even know if I still have this old document to go in and edit it. If I remember, I'll go through and try to find that. Now, here's the important part. This is what I really want you to take away from this. The capacitance here is 100% geometric. It only depends on the geometry, the area of the plates, and the distance between them. The amount of charge you can store on this positive plate here per unit volt only depends on the geometry. Even though Q by definition is, or C by definition is Q over V, that's like an energy density, a charge density. This is saying the amount of charge you can store up here on this positive plate per unit volt is proportional to the area and inversely proportional to the distance between them. See, if you increase the area, you can store more charge per volt. If you increase the distance, you can store less charge per volt. Purely geometric. It only depends on the geometry. Okay, so that's a parallel plate capacitor. That's one of the most common. In your computer right now, you probably have a couple. What are more common, though, are cylindrical capacitors. So you can watch all these videos and read all this on your own. What I want to point out here here's the formula for capacitance of a cylindrical capacitor. Again, depends only on the geometry. Capacitance is a function of geometry. Depends on the length of your cylinder and then the two different radii of your two cylindrical conductors. And again, you can watch these videos. These are not bad. Okay, now you've already watched the video on adding up capacitors in series and parallel. Next week we do resistors, and all the formulas are backwards. So when you add capacitors in series, we add them as reciprocals. When we get to resistors, resistors in series just add straight up. You just add them. And capacitors in parallel, we just add. Opposite for resistors. Resistors in parallel add as reciprocals. Again, I'm just doing a brief overview of the chapter. We're almost done. Capacitors are used to store energy. That's kind of the whole point here. It takes energy to squish those charges together. Remember, we got a whole bunch of positive charges on the positive plate, negative on the negative plate. They don't want to be there. It takes energy to squish those together. And this is how much energy I had to use up to get those charges together. Any of these formulas are equivalent. These all mean the same thing. So conversely, if I've already charged up a capacitor, this would be how much energy I could extract out of it. So I've got this thing charged up. I could now, I don't know, hook it up to some mechanical device, a motor or something, and this is how much mechanical energy I could get back out of it. Capacitors can store a tremendous amount of electrical energy. If you ever come across one of those old tube TVs that's been sitting around, maybe your grandparents up in the attic have an old tube TV. Never ever open it up and play with it. Those old giant tube TVs had huge capacitors in them that can store energy for decades. It still happens every now and again. You'll hear about somebody opening up an old TV that hasn't even been plugged in 15, 20 years and dying because they get shocked to death. I tell that story every semester. And one semester I had a student that went, yeah, that happened to me. Exactly like you're describing. My grandma had an old TV. I was poking around in it. And he said, it knocked me across the room. So never play with old TVs. So that's one application of capacitors, is storing energy. You can read that on your own. And then I want to skip to dielectrics. So we can take a capacitor. I'm going to kind of skip down to here. Instead of having a capacitor with a vacuum in between it, with the permittivity of free space, epsilon naught, we can stick some material in there called a dielectric. So this is a non-conducting material that still allows charge to flow a little bit. So it's mostly an insulator. So we stick material in here. I had a bunch of positive charges over here on the left. Because this dielectric material allows a little bit of charge to flow around, some of the electrons will drift over and try to hang out with these positive charges, leaving some positive charges over here. That decreases the electric field inside here, which decreases the voltage, which means I can get all these positive charges to hang out with less work. I have to apply a smaller voltage to get the same amount of charge on there, which means I can increase the capacitance. So the ability of that dielectric material to allow stuff to move around, we call the dielectric constant, K. Sometimes we call that kappa. And it's a ratio of the old capacitance to the new capacitance, or new to old. Here are some values for dielectric constants. So our reference point, the dielectric constant of a vacuum, we just let that be 1, and we measure everything in terms of that. So this guy here is 310 times more dielectric than a constant, which means he makes it 310 times better capacitor. I can store 310 times the charge for the same amount of voltage. Okay, so our electric field is going to be modified by this dielectric constant, which then in turn essentially modifies the permittivity of our new material. We call this new permittivity, instead of epsilon naught that we've been dealing with all semester, just new epsilon. That's our dielectric permittivity of this material. That's material specific. And it's just K, or kappa sometimes, times epsilon naught. And we get this new capacitance, which is our new, instead of A epsilon naught over D, we get A epsilon over D. We've modified the capacitance of our capacitor by shoving this dielectric in there. We make it much more capactive. Okay, and then the last thing I wanted to point out, where was it? Maybe I already passed it. No, I know it wasn't this far because I don't want to go into all that. Your touch screens work by augmenting the capacitance of the screen. So back in the day, they used to have physical touch screens where something would physically feel. They had pressure points, and it could physically feel when you were pushing on something, and that's how it knew where your finger was. Those were kind of crappy. The next kind of touch screens were resistive touch screens. By touching it, you change the resistance. But the kind we have now, your iPad, your phone, I know there was a great little video about it here somewhere. I don't know, it's here somewhere. You guys, I'm not going to make you watch me sit here and flip through. That's the way your phone works. That's how your touch screen works, is by touching the screen, you're literally changing the capacitance of the screen at that spot, and little sensors can measure that change in capacitance and know where you're touching.